Hello and welcome to this video on the superposition principle. If you haven't watched our previous videos on the superposition principle, I suggest going back to those first, where we cover the basics of the topic. But in this particular video, we're going to look at a more complicated example. And in this particular example, we're considering a battery charger. This is a fairly oversimplified representation, but let's suppose that we have two batteries that we wish to charge. So here they are, these two batteries or cells in this case, and we want to charge them by using this power supply of 100 volts. And so the intention is these batteries will eventually too be charged to 100 volts, but at the present one of them is only charged to 90 volts and the other to 80 volts. And the question in this case is to calculate the charging currents. So the current that's flowing through this particular branch of the circuit, I'm going to call it I2, and this current flowing through this branch of the circuit, which I'm going to call I3. Unfortunately, a question like this is more difficult than it first appears, because the current created by the potential V1 or supply is opposed by the potential of V2, and likewise for I3 is opposed by V3. And so we've got to use the superposition principle in order to evaluate a circuit like this. So just like our previous examples of the superposition principle, we start by eliminating all but one of our power supplies and evaluating the circuit in a more simplified sense. And then we'll move on to evaluate the circuit rather than just with one power supply. We'll evaluate it with a different single power supply, and then finally a third power supply. And at the end, we can superimpose all of these results together. Let's begin by removing two of our power supplies, in this case the two cells or batteries that are being charged, and replace them with a short circuit. I should say that we have some resistances in our circuit here, and they represent the impedances of the power supply and the two cells being charged in each case. So the power supply, we can suppose, has an impedance or resistance of 10 ohms. Our first cell being charged has an impedance of 20 ohms, and our third source, the cell being charged, has an impedance of 25 ohms. I'm removing the voltage sources, but I'm leaving the impedances in place. And we're going to evaluate this circuit simply now with only one power supply. To do that, we have to consider first of all the supply current that's leaving our supply V1. And so in this case, the current here I'm going to mark on as I1, and that's going to be our supply current. And that current is going to split into I2 and I3. And these currents should be fairly simple to determine because we now have only one power supply in our circuit. So to begin with, let's look at the total resistance in our circuit, beginning at the supply and moving through the circuit back to the supply. What we find is that our first resistance, R1, is 10 ohms, and then we reach a point where we split and go through either R2 or through R3, joining together back to the supply. And so what we find is our total resistance in this case is R1 plus R2 and 3 in parallel. So we can express that like this. We can say our total resistance RT is equal to R1 plus R2 in parallel with R3. That's just my shorthand for two resistors in parallel. If you're not familiar with calculating resistors in parallel, I suggest going back to the video where we do cover that. But in this case, putting some values in, we have 10 ohms plus 20 in parallel with 25 ohms. And that simplifies down to 10 ohms plus those two resistors in parallel come out as 11.11 ohms. And so our total resistance in this case is 21.11 ohms. Now we can calculate our supply current, the current I1 that's leaving our supply. Our 100 volt supply encounters a total resistance of 21.11 ohms, and so we can say that I1 is equal to our supply, 100 volts, divided by our resistance, 21.11. So Ohm's law being current equals voltage over resistance. And calculating that gives me a result of 4.74 amps. This current of 4.74 amps is going to split into two currents, I2 and I3. And so at this point, I'm going to use the current divider rule to evaluate those two currents as well. If you're not sure about the current divider rule, again, in a previous video, we've looked at that in more detail. I would suggest going back to that video first. But in this case, we're going to apply the current divider rule to split I1, which we know, into two currents, I2 and I3. And if we recall the current divider rule, the rule is to place the other resistor on the top of the fraction when we create our formula. Let's see what I mean by that. So in this case, let's work out I2, the current flowing through this central branch here. If I want to calculate I2, the formula would be I2 equals I1, the supply, multiplied by a fraction. And in this case, the two resistors in my current divider are R2 and R3. Some of the current is going to flow through R2, some of it's going to flow through R3. And like I said, the rule being whichever current that I'm interested in calculating, in this case the current flowing through R2, it's the other resistor that I'm going to put on the top. So in this case, R3 goes on the top. Both resistors added together on the bottom, R2 plus R3. Remember, it's only the resistors that are in the divider where the current's being split. So in this case, R2 and R3. I'm not bothered about R1 at this stage because the total of the current goes through R1. It's only when the split occurs. So that being said, I can put some values into my equation. We know that the supply current I1 is 4.74. I know that R3 is 25. And on the bottom I have R2 plus R3, 20 plus 25. And if I calculate that, I come out with a result of 2.63 amps. And that being said, now that we know that of the 4.74 amp supply, 2.63 of those amps go down here through I2. Whatever remains must be I3. So I could calculate I3 much like I've calculated I2. All I would have to do is change that resistor on the top. By putting R2 on the top, I'm now calculating the current I3. That being said though, I don't have to do that because I know that if 4.74 amps was the supply, 2.63 amps forms I2, whatever's left over must be I3. And so I can just do a simple subtraction here and say that I3 is equal to I1 minus I2. And putting some numbers in there, that's 4.74 minus 2.63, and that gives me an I3 of 2.11 amps. We've now calculated I1, I2 and I3, but unfortunately we've got to do that another 2 times because in our first set of calculations we only considered one of our 3 power supplies. We're going to do the same thing again, but taking into account our second and third power supplies individually. So in this second set of equations, we're now going to remove the first power supply and the third power supply. And so now we're only left with our middle power supply, V2. So I'm going to replace those with short circuits, much like I did before. And I'll also get rid of that notation for I2 there and just replace that with a wire for now. So we now have another circuit which only has one power supply. We're going to perform the same set of calculations again. So now our power supply begins here. We're going to do the same thing again, in that we're going to calculate the total resistance for this particular circuit starting at the power supply. So looking at this particular circuit now, we start at V2, we go through R2, the 20 ohm resistor, and then we split. We can either go through R1 or we can go through R3. And so our total resistance in this case, RT, is going to be R2 plus R1 in parallel with R3. Again, we can put some numbers in there very quickly. We can say that R2 is 20 ohms, and that would be 10 in parallel with 25 for R1 and R3. And 10 in parallel with 25 comes out as 7.14. So that's 27.14 ohms as a total there. Now that I know RT, I can calculate the supply current, which in this case is going to be I2. Again, I'm trying to be quite consistent in what I call I1, I2 and I3. That becomes important at the end. So any current in this branch I'm always going to call I1. Any current in this branch I'm going to call I2. And any current in this branch I'm always going to call I3, regardless of which set of equations we're doing. So in this case it's I2 that I'm going to calculate first, and as you suspect, I2 is going to split into I1 and I3, but we'll get to that in just a second. So to begin with, I2 is going to be our equation for Ohm's law, and in this case V over R is going to be 90 over 27.14, and that gives me a current I2, our supply current in this case, of 3.32 amps. So my current I2 is 3.32, and again we're going to use the current divider rule to split that 3.32 amps into I1 and I3. Let's begin by calculating I1, the current that flows down this branch of the circuit. And so again we can apply our current divider rule. We can say that I1 equals I2 multiplied by a fraction, and remembering our rule for the current divider is that if I want to work out the current going through R1, then I have to put R3 on the top of the circuit, the other resistor in the divider, which is these two resistors here. So R3 is going to go on the top, even though I'm calculating the current going through R1. So it will be R3 on the top, R1 plus R3 on the bottom. And so as a result, putting some numbers in, we can say that that's 3.32, which was our supply current I2, multiplied by a fraction, R3 going on the top, so that's 25, R1 plus R3 on the bottom, 10 plus 25. And calculating that gives me a result of 2.37. That's in amps. And again, it's easy to calculate I3 now. We know that 3.32 amps flows out of our power supply. 2.37 of those amps becomes I1 flowing down this way, and the remainder must be I3. And so I can simply say that I3 is going to be I2 minus I1. Putting some numbers in, 3.32 minus 2.37 gives me an I3 in this case of 0.95 amps. Finally, We only have to do this one more time. We have evaluated the circuit taking into account V1. We've just done it again for V2. We're going to do it one more time for V3. And so the same thing again. We're going to remove our power supply V1. We're going to remove V2. And now we're just left with V3. And so I'm going to replace those two branches with short circuits. I'm also going to remove this little notation here for now as well. We have our third circuit to evaluate, and we're going to do the same thing again very quickly. Hopefully we're getting the hang of it now, and we'll see that in this case our T is going to be 25 plus 20 in parallel with 10. We're flowing through the 25, splitting into these two, R1 and R2, which are in parallel, and so we end up with a total resistance of 25 plus those two being in parallel, which is going to be 6.67, which gives me a total of 31.67 ohms. Ohm's law is going to give me I3 this time, and I3 is going to be 80 divided by 31.67. That comes out as 2.53 amps. And in this case it's I3 that's going to split into I1 and I2. So I'm going to use the current divider rule one more time to evaluate those as well. So let's say that first of all I want to calculate I1, the current flowing through R1. I know that I3 is 2.53 amps. It's going to split into these two currents, and of these two I'm going to calculate I1. And so remembering the current divider rule, it's R2 of the two dividers, of the two resistors in the divider. R2 is going to go on the top of my fraction, and so I1 is going to be expressed as I3 multiplied by a fraction. R2 goes on the top, R1 plus R2 goes on the bottom, and so we end up with 2.53 multiplied by 20 over 10 plus 20, and that comes out to give us an I1 of 1.69 amps. Again, I2, the one remaining current, is just going to be whatever the supply was, I3, multiplied, subtracting I1, and whatever remains, in this case 0.84 amps, is going to be my current I2. So finally, we have now evaluated our circuit here 3 times, taking into account each of the 3 power supplies. The final step is to superimpose or bring together all of our results. To do that, let's go back to our original diagram here. And what I'm going to do is I'm going to try, if I can, to notate all of the currents that we've calculated onto one diagram to bring them all together. Let's start with the first set of currents that we calculated. If you remember, we removed both of these cells so that we're left with only the V1 as our power supply, and we calculated I1 splitting into I2 and I3. Let's mark those on here. So taking into account their direction as well, we had our current I1 splitting into I2 and I3 going back to the power supply. And just to squeeze some values on there, we said that I1 in this case was 4.74 amps, and that's split into 2.63 amps and 2.11 amps. The second time we considered this central cell as our power supply, the current flowed up and split into 2 currents flowing down, I1 and I3. So I'm going to mark those on here, pointing upwards and downwards respectively for I1 and 3 there. And those values were 3.32 amps, splitting into 2.37 amps and 0.95 amps. Finally, if I can squeeze them on, we evaluated the final cell on the end here. The current would go up and then come down through these two branches, 1 and 2. And so we can mark on their direction, going up for I3 and down for I1 and 2. And we found that it was 2.53 amps that split into 1.69 amps and 0.84 amps. So you'll find that I've done two things. First of all, I've put all my values on the same diagram here, but I've taken into account their direction. And so finally, the last step is to total these currents for I1, I2, and I3. Now the question, if you remember, was just to calculate the charging currents. Really, we were only interested in I2 and I3. But in this case, we're going to calculate all three. To do that, I'm going to take a convention of assuming that upwards is positive. So if our currents are upwards in their direction, I'm going to call that positive. If they're downwards, I'm going to take them as being negative, just to make this last evaluation a little bit simpler. So just on the side here, we can calculate our total I1 to begin with. And what I'm going to do is say that anything upwards is positive, anything downwards is negative. So that would be 4.74 as a positive, minus 2.37, minus 1.69. And that gives me a total I1 of 0.68 amps. I can determine a total I2 very similarly. So the total I2 in this case would be minus 2.63 plus 3.32 minus 0.84. And that gives me a total of minus 0.15 amps. Lastly, the total I3 is equal to minus 2.11 because it's going down, minus 0.95, also going down, plus 2.53 going up. And that gives me a total of minus 0.53 amps. So our final evaluation of this circuit is that 0.68 amps flows out of our supply, 0.15 amps flows down through V2, and 0.53 amps flows down through V3. And so our charging currents, I'll just make a note at the bottom here, our charging currents are 0.15 amps and 0.53 amps respectively. So I hope you found this video useful on taking the superposition principle and applying it to quite a complicated example, but using it to evaluate the currents in a more complicated circuit.